pre-calculus students, today we are going to talk about 413. So we're going to talk about figuring out the degree from looking at a graph, how many real roots, how many imaginary roots we'll also talk about, and how to figure those out by looking at an equation. And then if I'm given the roots, how to write the equation. So here, looking at part A, we talk about the degree. When we first started this chapter, we would talk about, okay, well, the number of x-intercepts is the degree. And we also talked about, when we have both ends facing the same direction, that it's even. And this has 3 turns. So we can also think of it as the number of turns plus 1 is the degree. But here we can really see there are 4 x-intercepts. We would say here the degree is 4. Now, when you look at graphs D and G, you can see they're the exact same graph. They've just been shifted. Okay, so the degree is still going to be 4, but the number of real roots is different. The number of real roots just means the number of x-intercepts. So that word real is going to mean it hits the x-axis at a real number, so not an imaginary number. So here this has 1, 2, 3 real roots. Okay, this one we would say has 1, 2, 3, 4 real roots. And the difference here is that this one bounces. And remember, when you have a bounce, that means that it's a double root. So we've got 1 double root. So that accounts for like 2 when we count degree, and then 3, 4. That's how the degree is still 4. All right. Now in this one, same graph again. So the degree is 4, but now it's only hitting the x-axis 1 time. Okay, so if it's only hitting the x-axis 1 time and the degree is 4, that must mean that there are 3 imaginary roots. All right, so let's take a look at this next one. So when we look at part B, I see that one I know it's a parabola. It's got to have a degree of 2. And in this case, I see it hits the x-axis 2 times. It has 2 distinct real roots. And again, these are the same graph, just shifted. And this one is hitting the x-axis only 1 time. Now, the degree is still 2. It has 1 distinct root, but it's bouncing, and so it's a double. Okay, so that's where that's how looking at that we can know it's a degree 2. That's a double. All right, this one still degree 2, but in this case, it's never hitting the x-axis. So it has no distinct real roots. So that means because the degree is 2, it must have 2 imaginary roots. All right, and then this last one, when I look at C, okay, and I know that this is cubic, right? We've talked about the shape of a cubic. You got one end up, one end down. So the degree is 3. It's got these 2 turns, and it hits the x-axis 3 times, so 3 distinct roots. In this case, because there's a bounce right here, it's only hitting the x-axis twice. So the degree for all of these is still 3 because same thing, right? It's the same shape, just shifted, but here it's only hitting the x-axis twice because there's a bounce. So that means, oh no, yeah. So this is counting for 2 and then 1. All right, so there aren't any imaginary roots in this one. Just because this is 2, it doesn't mean there's 1 imaginary, because that's a bounce and that counts for 2 of them right now. But in this one, it's only hitting the x-axis once. And notice if something's odd, it's always got to hit the x-axis at least once because it's 1 end up and 1 end down. So it has 1 real root, and because this turn isn't on the x-axis, that means that there must be 2 imaginary roots to make a total of 3. So that idea that the degree has to do with the number of roots is the fundamental theorem of algebra. A polynomial of degree n has n complex roots. And remember, any real number is also considered a complex number. So complex numbers mean they have an imaginary part. Right here, you can see that the 3i, the 7i, the minus I. Okay, but these you don't see an I to them. Well, you could just rethink of it as plus 0i. So it's still that same idea. All right, so next we're going to talk about how can we determine the roots of a polynomial. And when we talk about that word roots is interchangeable with the solutions. And the solutions are what x values make the y value 0. So sometimes they're also called zeros, and your real solutions are x-intercepts. So they also show up in your graph as x-intercepts if they're real numbers. All right, so determine the roots. So if I want to figure out the roots of this, first of all, I look at it and I'm like, well, I definitely can't factor it. So what we did before, if I want to know, like, what are all the things that multiply out to be this, I want to know what all the factors are. And if I had something like, let's say, I want to know all the factors of 432, I would look at that and say, well, I know 2 goes into it. And so then I would do 432 divided by 2, and then I would take that and say, okay, well, now I'm going to break down the 216. So I want to use that same idea here. If I could know a factor of this, then I could divide by that factor, and then I could take whatever's left and go from there. So we talked in sections 411 and 412 that the x-intercepts, the real x-intercepts, can be written as factors. Like if I have an x-intercept of 1, the factor is x minus 1. So what I want to do is I want to look at the graph of that equation. So let's bring that over here. Here's the graph. So looking at the graph, I see I have an x-intercept right there at 1. So if I have an x-intercept at 1, so from the graph, there's an x-intercept at 1, then that means I have a factor of x minus 1. And what I'm going to do is I'm going to divide that p of x by my factor. I'm going to divide p of x by that factor of x minus 1. So I'm going to set up my box. Now, some of you might be thinking, okay, but like you never let us have a graphing calculator on a test. So what are we supposed to do? All right, so what would happen is I would either give you the graph so you can see the x-intercept, or I would just straight up say the x-intercept is blah, and then you could use that to write the factor. All right, so yeah, you're right. We haven't let you have a calculator on a test. At some point we will, but we're just not there yet. All right, so I put the x cubed here. What times x is x cubed? So that's x squared. X squared times -1 is -1x squared. Okay, my x squareds have to add up to be 2x squared. So that means that this has to be a 3x squared. So these add up to be 2x squared. So what times x is 3x squared? That would be 3x. And then times -1 is -3x. My x's have to add up to be positive 2x. So this would have to be a 5x. So what times x is 5x? This is a plus 5 times -1 is -5. Oh, and that's what I needed. Okay, so think about when you divide by a factor, like with regular numbers, it should go in evenly. You should have no remainder. So that's the same thing here. You should have no remainder. If you come up with a remainder, it means that you did something wrong with your arithmetic here, or maybe like you said, this was x equals 1, and then you wrote x plus 1 instead of x minus 1. Remember, like these are opposites here. So if I want to find all the roots of the zeros, I want to know what makes this equal 0. So I have one solution right here. So then to get my remaining solutions, I have to set this quotient equal to 0 and solve. All right, so this whole thing up here factored into, should write this really, x minus 1 times this. So I get one solution from this, it's just x equals 1. Now I need to set this equal to 0 to get the other solution. Okay, that's not factorable. Right, there aren't numbers that multiply to be 5 and add to be 3. So I'm going for my quadratic formula. So the opposite of b, so -3 plus or minus the square root of b squared minus 4 times a times c all over 2a. And if I think back to what my graph looked like, it only had one x-intercept. So here it is again, there's only one x-intercept. It's cubic, I should expect 3 solutions. There's only one x-intercept. I should expect my answer to have imaginary numbers in it. So this is 9 minus 20, which is -11 over 2. Okay, remember with the square root of something negative, you can rethink of that. -11 is the square root of -1 times 11, and the square root of -1 is I, and remember we know that I squared is -1. So you could think of this -1 as I squared times 11, and the square root of I squared is I, and then I can't take the square root of 11. In general, when you have the square root of a negative number, it's always just I times the square root of what that number is. If you can take the square root of this, like if this was -9, I could just say this is 3i because I can actually take the square root of 9. Here, I can't take the square root of 11, so I just leave it alone. You could put the I in the front or the back. I usually put it in the front because otherwise, if I put it in the back, sometimes I'm sloppy and it's unclear. You have to be really clear that your I is not under the radical. Okay, and sometimes I'm sloppy about that just with my handwriting. And so I just write it in the front. Okay, now this gives me two solutions. So here's my one solution here. This is one real. This is two imaginary, right? Because this can be split into the plus and the minus if it helps you to see the two solutions better by splitting it, right? There's a second solution and here's your third solution, right? Because we should have three. Okay, there's the two imaginary right there. You don't have to separate it though. And it can't be simplified, so you just leave it alone. All right, so let's take a look at this next one. And for this one here, again, I'm going to look at the graphs. Let me turn this one off. I have this one all set up, ready to go. Okay, so I look at this one and I see I've got this one here. Oh, can't tell, do I have, it looks like it's going slightly over here. All right, so let's see. This is at 0.2618, but there is, okay, hang on. There's a point here at 0.5, there's a point here at 0.382, and then there's a point here at 2.618. It's cubic, so I should expect three things, and look at all three of them are just showing up on the graph. Okay, so I'm going to drag this over because I'm not going to remember them if I look away here. So 0.382, 0.5, and 2.6. So this one, from the graph, there were x-intercepts at 0.5, 0.382, and 2.618. Those are the x-intercepts. So if I want the roots, I mean, then those, whoops, I don't know what I just did there. Then those are the roots. Okay, so if I graph the x-intercepts, this is where it hits the x-axis. Those then are the roots. All right, so sometimes, I mean, it just works out like that. We won't put one like that on the test because we wanted to see that you can do this process. But I mean, that still, I mean, that gives us the roots. So I don't really have to do more for that one. All right, so we've got one more here. And I have this here. In general, if a polynomial is not factorable, you're going to graph to find an initial root or one will be provided. Like on a test, you're going to write the root as a factor, divide to find other factors, set the factors equal to 0 to solve. You may need to use a quadratic formula. All right, so let's take a look at this one. This one I did make a little bit where we actually are going to have to go through that process. All right, so it's cubic, but it only has one x-intercept here at, looks like 3. Yep, got 3. So let me get this out of the way. Okay, so let's see, x equals 3 is an x-intercept. So that means x minus 3 is a factor. So we're going to divide. This is x cubed here. So this would be x squared. This would be a minus 3x squared. My x squareds have to add up to be negative 5x squared. So this would be negative 2x squared. This would be a minus 2x. Negative 2x times negative 3 is 6x. 6x plus what is 23x? This would have to be 17x. So it would then be plus 17. 17 times x is 17x. And then 17 times negative 3 is negative 51. Again, I should have no remainders. So the factors are x minus 3 and x squared minus 2x plus 17. Okay, the solution from this is x equals 3. The solution from this, I'm going to have to, it's not factorable, right? Numbers that multiply to be 17 and add to be negative 2x, nope. So x equals the opposite of b, so 2 plus or minus the square root of negative 2 squared. Make sure that negative 2 is in parentheses and squared. This and this mean two different things. This means negative 2 times negative 2, that's 4. This means the opposite of 2 squared, that's negative 4. If you write this and say it equals 4, that's not correct. This isn't correct, and saying that this equals 4 is not correct, okay? You need to write it like this. Okay, so minus 4 times a times c all over 2a. So this is 2 plus or minus, that would be 4 minus 68, which is negative 64, all over 2a. Okay, so square root of negative 64. Remember, I had said if you have the square root of a negative number, that equals I times the square root of that number. So if I have the square root of negative 64, that means I times the square root of 64, and the square root of 64 is 8. So that's 8i. So this is, did not leave myself enough room here, 2 plus or minus 8i over 2. Okay. Now, some people are like, whoosh, I'm going to cancel out these 2's and say it's 8i or something like that, or say 1 plus 8i. You have to divide both of these by 2. It's like we've done lots of stuff where we have a common denominator, right? If I gave you this, you'd say, okay, I'm going to keep the 2 and add across the top, right? So it's like I'm splitting this up. So 2 divided by 2 is 1, plus or minus 4i divided by 2, or 8i divided by 2 is 4i. So there are my 2 imaginary solutions. Here's my 1 real solution. Okay, so you need to have all of them. If this can be simplified, you need to simplify. Okay, in this one, there was nothing that's simplified. This one there is, so you need to make sure you do it. All right, now going the other way, if I give you the roots, and now I want the polynomial. So if I know C is an x-intercept, or a root, I should say, then x minus c is a factor. So that's the idea we're going to use here. So if c is an intercept or a root, then x minus c is a factor. So this right here, I could write as x minus negative 3 plus I times x minus negative 3 minus I. Notice I'm putting these in parentheses because this subtraction has to go to everything. All right, so this would be x, this would become plus 3 minus I, and then this would be x plus 3 plus I. Okay, notice that the real parts are the same and the imaginary parts are opposites. Those are called complex conjugates. So these are complex conjugates. And if one imaginary number is a root, that means that also its complex conjugate is also a root, because when you square them, you get the same thing either way. Okay, so these are complex conjugates. These are just called conjugates because they don't have an imaginary number. Conjugates, I can't spell conjugates. But this part is the same, the root part are opposite, those are called conjugates. All right, so then I need to multiply this out. So I'm going to do a 3 by 3. I actually don't love this. I think this just gets long. There is another way to do this that we learned about in class, and we'll talk about that in a second, which I think is faster. But some people just like this method better. So I'm going to show it. So all the things with the i's end up working themselves out in the end. And that happens because they're conjugates. Okay, so these go. We know I squared is negative 1. So this is the opposite of negative 1. So this is the same thing as a plus 1. So if it says write an equation, make sure you write an equation. So this would be x squared plus this would be 6x. And then 9 plus 1 is 10. Okay, so that's one way to do it. The other way to do it is if I know like before when I say I know x equals 3 is a intercept, then to get the root, really all I'm doing is I'm subtracting 3 and saying x minus 3 equals 0, and then there's my factor. Okay, I can use that same idea with these. Okay, so if I know that negative 3 plus I is a root, I know x equals negative 3 plus I. And then what I could do is I could move these over to make the factor. But instead of moving both of these over, I'm going to just move over the 3. And I'm going to get x plus 3 equals I. And what I'm going to do, and I did that because I know if I square I, it's I squared. Here, if I square this, it's a little bit more work. But here, if I square this, I squared is negative 1. And if I square the x plus 3, like make a box, and square the x plus 3, not just square the x, square the 3, but you get x squared, 3x, 9. So you get x squared plus 6x plus 9. And then if I want, remember, I want 0 on the right. If I add this 1 over here, look at, I get the same thing I got over there. And to me, that's a lot faster. Now, some people are like, well, why didn't you have to use the other one? Why didn't you have to use the -3 minus I? Okay, so look at what happens. I add the 3 over, I get x plus 3 on the left, and then I have -I over here. Watch what happens when I square. Whoops, that was just, sorry, I got a little excited there, but with the squaring, got a little ahead of myself. Okay, so I added the 3 and then I have this -I and I square it. Well, when I square the negative, it's positive. So it just comes out to be I squared. So you see, I get to the same point as I was at right there, which is going to give me the same result. So it really doesn't matter which one you use. If they're conjugates, this would give you both of these out as solutions. Like it will give you this and this solution. So it doesn't matter which one you use. To me, this is a lot faster than this. Okay, but you get the same answer either way. And this idea here works also on radicals. So let's start the radical one that way. If x equals 5 plus root 3, and I want to get the factors, I could subtract these both over and then go through the deal I did here, or I'm going to just subtract the 5 and get the radical by itself, because it would be easier to just square the radical. And then I'll square both sides. So this is just 3, and over here, this would be x squared minus 10x plus 25. And then I subtract the 3, so it'd be x squared minus 10x plus 22 equals y. All right, and same as with the complex, it wouldn't matter which one you picked. So because if you're like, well, I didn't do anything with the other one, because they're conjugates, it doesn't matter, because right here, when you square, right, you're going to get a 3 here, you're going to get the same, you're going to get the exact same thing. Okay, so I don't need to do it twice, I get the same thing. So here is my answer. Now, if you're like, I don't like that, it doesn't make sense to me, then you could write them as factors. So you could do x minus the 5 plus root 3, and then x minus the 5 minus root 3. Let me just make sure I wrote those down the right. Okay. Okay, and then you would have to do x minus 5 minus root 3, and then x minus 5 plus root 3, and then make the box multiplied out. Like I said, I think this takes a lot longer. Some people like it. You don't have to be able to do it both ways. I'm just showing it both ways. Because, like I said, some people like doing it one way, some people prefer the other way. Do what works for you. Whoops. It's not what I wanted, is it? Minus 5 plus root 3. Okay, so this would be x squared minus 5x. And then this would be x root 3. Again, all the nasty radical stuff will work itself out. This is minus 5 root 3. This is minus x root 3. This is plus 5 root 3. And this is minus 3. Okay, so again, those go, and then I would have y equals x squared minus 10x, and then there's my plus 22. Okay, same thing that I got when I did it up here, but I just feel like that took way less time. Okay. I hope that helped. Have a good day.